we said draw a ladder die schematic that consists of 3 light bulbs. 2 light bulbs wired in series. The third is in parallel to the 2 in series. A single pole switch controls the whole 120-volt circuit. A second switch will bypass the second bulb in the series circuit when closed. Okay, so this is a very simple schematic consisting of a parallel and a series circuit, and then a bypass. Okay, we don't see it used often, but a bypass is used very often in oil, in the primary controls. That's why I wanted to talk about
I can't see any video. Can anybody see any video?
Oh, I'm sorry.
Negative.
That's my fault. No, you guys weren't seeing video.
No worries.
My apologies. Okay.
Thanks, Cody.
Better?
Got it.
Okay.
Perfect.
Sorry about that. So again, we had the bypass. Okay, and it's not used very often in HVAC. Okay, we basically use it in a couple different spots. Sometimes in electric heat, we use it a little bit in a few air conditioning controls, and we use it very heavily in the primary control, which is our safety of the oil burner. We use a bypass. So that's why I wanted to introduce the purpose of the bypass. So this was our basic circuit. Does anybody have any questions or anything I need to go over on this basic circuit? Please notice my labeling. Please notice how it's drawn in a ladder format. So we have our outside rails, which is my line and neutral. We have my rungs of the ladder, which all have a load on it. You cannot get from line to neutral without a load. Any questions on that?
No, sir.
Okay. I really want to make sure that as we go through this, if there's questions, let's get them out of the way. Okay, so our next schematic of the day, we took the same diagram, basically. So I'm just going to, since I don't feel like drawing everything out, I'm going to come down here to my second schematic of the day. It's basically a modification of this diagram. Okay, we said draw a ladder diagram, again, ladder line voltage schematic, that consists of 3 light bulbs. 2 of the bulbs are wired in series, third wired in parallel. A single pole switch controls the whole 120-volt circuit. A second 24-volt switch will bypass the second bulb in the series circuit when closed. I said add any additional components that we have discussed that you need to make this work. What additional components do we need to add to make this work?
Transformer.
Yeah, your primary component we need to add is a transformer. Okay, what else are you going to need to add?
Relay coil.
And if I have a relay coil, you say that again?
A relay contact as well.
Yeah, if I have a relay coil, I got to add a contactor. So let me grab my transformer. And again, if you guys have not started drawing a schematic sheet yet, I probably would. It makes it so much easier in the long run. Okay, so I'm going to, first thing I'm going to do is I want to get my transformer in. Okay, now why does my transformer go here? Okay, I've seen a couple people submitted transformers in various places. Why does my transformer need to go here? Anybody want to guess? I saw somebody, a couple people submitted a transformer where I have my SW switch. Why does it need to go where I have it rather than where my SW switch is?
I have no idea.
If I put my transformer up here in place of my SW switch, is it ever going to get full source voltage?
No.
No, because it's in series with B2. So it really, the transformer needs to get full source voltage. The only way it can get full source voltage is going between line and neutral. Nothing else in the path of my coil, of my primary side of the transformer. Very important. So down here on the bottom, okay, I need to put in a switch. Basically, I'm going to move my switch from up there, okay, because I need to put in my 24-volt switch. I'm no longer dealing with a line voltage switch. So let's go ahead and draw in the change to this circuit. Okay, coming out of the switch, what do I need to have?
Your relay coil.
You have a relay coil. Okay, well, since I don't like drawing things over and over and over again, oops. Amazing, it worked that time. Okay, so I'm going to come down. Now, relay coil always gets connected back to what?
Your common.
My common, yeah. Now, the other thing that I saw a couple people do, and it was actually, yeah, it was a couple different people that actually, let me get rid of that spare relay up there. Don't know how that happened. They connected my relay coil back to neutral. Okay, a couple people took your relay coil and connected it back to neutral. Why doesn't that work?
Because it needs to be 24 volts, not 120.
Yeah, we never want to cross the 24-volt side with the 120-volt side. Okay, you've got to be very, very careful about that because you can melt down components that way. Okay, so now up here, I'm basically going to draw I'm going to draw my normally open relay contact. Connect that in. What am I missing to make this schematic complete?
Thermostat.
This one didn't say a thermostat. That was the other. That's the next one. What am I missing here to make this schematic complete where it would be acceptable?
Labeling.
Labeling, right? Because if I had more than one relay in here, I'd never know what relay coil controls what relay contact. So I got to be very careful. Everything needs to be labeled. Okay? It's really important as the schematics get more and more complex. So we know that this relay coil controls this set of contacts. Does anybody have any questions on this diagram, and including the bypass? Okay? Any questions on the sequence of operation? Okay, somebody give me the sequence of operation for this diagram. What happens after I close SS and close SW? Tell me what's going on.
First, bulbs 1 and 2 are energized with 120 volts. The transformer gets energized, closes the switch, and energizes the coil, which will light up bulb 3.
Close. Let me say this in a slightly different way and see let's see the comparison.
Oh, yeah,
I close switch SS, I energize the transformer primary as well as bulbs 1, 2, and 3. 2 and 3 are getting partial voltage, so they're a little bit dim. I close switch SW, energizing the coil of RC. RC normally open closes, and bulb 3 is no longer powered. Bulb 2 is getting full source voltage.
Makes sense.
Okay, the big difference is in what was just said is that bulb 3, when you first energize this circuit, when you close SS, bulb 3 is actually getting power because this normally open is open. Okay, bulb 3 gets turned off or bypassed when we close SW and energize RC. That's the big difference. Okay, this was schematic number 2. Okay, now, I have several people in the class, and again, I'm not going to name names on a call. It wouldn't be right. I value your guys' privacy a little bit too much on that. But I have several people in the class who are turning in schematics that makes me think that you might have an electrician background. Okay, some of the schematics you're turning in to me shows more what an electrician would be drawing for wiring diagrams. Okay, when we're talking ladder schematics, I need to have a schematic that has the outside rails, which will be the line or neutral, or on the low voltage side, my power and my common, and the loads and the switching devices go across on rungs in the rails. Okay, so again, I know some people in here have some electrical background, and I think you're drawing things the way you may have been taught with an electrician course. That's fine. But for ladder diagrams, I really need to have it drawn in this manner. Okay, and again, please refer back to the syllabus for the standards on this. But it's sort of important because this allows us to look at sequence of operation. Now, schematic 3 was a little bit differently. Again, it's built on what we've already done. Okay, so if I take a copy of this diagram, okay, and if I go down a little bit more to where I had schematic 3, and I'm giving those of you who are on this call this morning sort of a gift with this, schematic 3 basically said, draw a line voltage schematic that consists of two light bulbs, okay, 2 bulbs wired in parallel. A single pole switch controls the whole 120 volt circuit. A 24 volt thermostat controls bulbs 1, and a 24 volt switch controls bulb 2. Add any additional components that we've discussed to make this work. Okay, so I got to alter the schematic a little bit because I no longer need a bulb 3 and I no longer need this bypass. Okay, because it's no longer asking for that. So we're going to get rid of bulb 3. Okay, I'm just going to move things over a little, well, hopefully move things over a little bit. I'm going to move things over a little bit here. Okay, get rid of my, well, not get rid of, I think I'm just going to drag it off to the side because I'm going to use it. Okay, so again, I have a single pole switch that's going to control bulb 2. I have a thermostat that needs to control bulb 1. So, what do I need to put in series with bulb 2 to make this work? Anybody?
The contact?
The contact, right? So if I take that line out, okay, now I have a single pole switch that's controlling bulb 2. Okay, now to control bulb 1, based on the directions, what do I need to add? What do I need to add?
Thermostat.
Need to add a thermostat and there's something else.
Another contactor.
Yeah, another relay or contactor. So what we're going to do, basically I have another relay coil I need to put right under this. Let's do this the easy way. Don't do extra work if you don't need to do extra work. Extra work lets you forget things. So we're just going to extend this down because, again, we know anything I do has to come back to common. Can I have this relay coil named the same coil name as I have the other one?
No.
No, I got to change it. I'm just going to change it to HR, and I have a reason for that, okay? Now, what do I have to do up here in line with bulb 1? What goes in here?
Add the second contactor.
Okay, another contact. I did hear someone say thermostat. Thermostat we're going to put on our low voltage side.
Yeah, I just realized that the thermostat goes on the bottom. That would make sense to put it there. Gotcha.
Okay, so I'm just going to copy that, and I'm going to throw it up there. Now, can I leave the designation RC on this one?
No.
Have to change it to match this, right?
Mm-hmm.
Have to change it to match the HR. This is why labeling becomes important, by the way. Okay, now I'm missing one component down here. What am I missing?
Your thermostat.
Yeah, got to put that thermostat in. Okay, well, what type of thermostat are we going to use in the oil term as our primary control thermostat? What am I using?
The heating thermostat.
Yeah, my heating thermostat. Okay, so I'm going to go ahead and just grab my heating thermostat. Okay, and I'm just going to extend that line down. Now, we do need to do a few little labeling things here for this to really look good. I'm gonna just label that HT for heating thermostat. We talked about wire connections on our thermostats yesterday. I would want that labeled R and W. What is the sequence of operation on this diagram?
Line voltage is given to the transformer, which then you close the switch powering your coils, your RC. RC powers bulb 2, and once your heating thermostat satisfies, your HR powers bulb 1.
Okay, heating thermostat satisfies, you're very close, but heating thermostat satisfies or heating thermostat calls?
Calls, sorry.
Okay, yeah, satisfies, when you're talking a thermostat, satisfies puts it back in the open position. Calls keeps it on it's closed, it's calling for heat. Okay, yeah, that was exactly right. Service switch is closed, provides power to the 120 volt primary of the transformer, okay, which in turn allows the 24 volt side to get power. When SW switch is closed, the RC coil is energized. RC contact closes and powers bulb 2. When the heating thermostat calls for heat, it closes R to W, powers the heat relay HR, which closes the contacts HR and powers B1. Folks, this is the circuit that everything else we do in oil is built from. Okay? This is the first part of the oil control circuit. That's why this circuit's so important. From here on in, what we do is we start adding components. Obviously, we're not going to use light bulbs for our, a light bulb doesn't provide enough heat. We're not going to use it for a burner motor. A light bulb doesn't have the power to blow air around a house. We have to change out motors. But this diagram up here is your primary and basic oil control diagram. Any questions before we move on? I'm going to start talking about motors. Anybody who's copying this down, you got it?
Got it, and no questions.
Okay. Everybody who's copying this down, especially if you're taking screen prints, please draw it on your own. Don't just submit your screen print for Schematic 3. I've seen my diagrams before. Somebody actually on Schematic 2, when I went over it the other day, grabbed a screen print of it and uploaded my screen print. Don't do that. It's not cool. Okay, so this is where we're going to move forward from. The first thing we're going to do is we are going to talk about some motors. Now, here's the situation with motors. What I'm going to do today is give you an overall view of motors so that we can understand what's happening in the oil burner. We're going to dig much more into depth on I think it's on Friday or Monday, into motors. But I want to give you enough of motors, and unfortunately we have to mention capacitors. I can't get away from it, where we have an understanding of what these different diagrams are doing. Okay, without having the understanding of the diagrams, it's very difficult to have the conversation about motors because you really don't know what it's supposed to be doing. So we're going to go into, I'm going to show you what I consider a connect-the-dot diagram. Okay, it's a pictorial wiring diagram. I'll upload it to your course later, but I want to talk about it right now. So what we're going to talk about, and again, this is just, again, we have a thermostat, we have a capacitor, and we have a motor. Now, some of you guys already know this, but bear with me while I go through it again. Most of the motors we deal with in the HVAC industry have two windings. One of the windings is considered a start winding. One of the windings is considered a run winding. Okay, the run winding has less loops of wire because it's a winding, so it's just coils of wire basically. The run winding has less coils of wire and the wire's a little bit thicker than the start winding is. The start winding has a lot of coils of wire and is much thinner wire. The start winding is not powered constantly with full line voltage. Okay? The start winding is either taken out of the circuit once the motor starts or has a capacitor in series with it. And that will make more sense when I start wiring this stuff. Now, a motor has three terminals. Okay, we have a terminal that's basically right there, and right there. If you have the resistances on a motor, like this one has a 5 ohms and a 14 ohms, your run terminal is always the lowest resistance. Okay? The start terminal will be the highest resistance if it's printed in this way. So even though in this diagram run and start is not labeled, you know, because you'll always know that your run terminal is the lowest resistance between run and common. Your start terminal is the highest resistance between run or between start and common. Okay, any questions on that?
Nope.
Now, if you get to something where a motor is not labeled, okay, let's say you have 3 wires just dangling there because Happy Homeowner did a do-it-yourself project and had 3 wires just hanging there. It happens. Okay, 3 wires. Okay, what you're going to do is you're going to take a resistance reading between the ends of each of those 3 wires. Okay, so let me just, I have 3 wires. Okay, each wire has an end. Okay, you're going to take a resistance reading, let's say between the first 2. Okay, your resistance reading could be a 14. Then you're going to take a resistance reading between the second two. Okay? And let's say your resistance reading at that point is a 19. Then you have one more resistance reading you have to take because you still have your third combination. I'm going to take a resistance reading from my two outer ones between each other. Okay? So now I have a resistance reading of 5. Okay, look at the above look at the above motor, the one that has that I've labeled SR, and there was a pre-label of C. Do these numbers make sense based on what we're seeing on that motor up there? Okay, my resistance reading where I'm getting the 14, okay, is between start and common. The resistance reading where I'm getting the 5 is between run and common. Okay, the resistance reading where I'm getting the 19 is actually going from start to run. Okay, so when I look at these resistance readings, okay, I know that common is not one of these two terminals. Okay? So it's not one of the bottom two terminals is not common. Okay? Because I'm going from start to run as my highest resistance reading because I'm taking both windings together. So I can tell you right now, it's not, these two terminals are start and run. So then I have to look for where my next highest resistance reading is. Okay, which is my 14. Okay, I can tell you right now that this terminal right there, okay, that terminal right there is my start. Because my next highest resistance reading is start to common. If I know that this terminal is start, and I've already ruled out that this terminal isn't common, I can tell you right now that that terminal is run, and that is C. It all has to do with the math. When you take a resistance reading from start to run, you're going through both windings, so the numbers are going to add up for your total. So again, if you get a motor that's not wired and you have 3 leads sitting there, you can always find out by using your ohm meter what start, run, and common is. Does anybody have any questions on that?
No, sir.
Okay. By the way, that's something you're going to use in the field. That's something you're going to use in the shop when you guys get back into class and start doing the shop projects in the shop. That's one of the labs. Okay. So let's wire our motor here. Let's wire our diagram. There's 2 rules with motors that you can always remember. Run winding always gets full power. Okay, the run winding always gets full power. We don't put anything, 99.9% of the time, there's nothing in series that's a load with the run winding. So when I'm wiring this, the first thing you want to do is A, power your thermostat, okay, and then come out of your thermostat with line, okay. Your run winding always gets line voltage There's nothing ever in series with your run winding. Your start winding, on the other hand, if there is a capacitor, the start winding always is in series with the capacitor. And I'll explain why in a minute. But the start winding is always in series with this capacitor. So what we do is we put the start winding in series with the capacitor. Common always comes back to neutral. Okay, so I'm going to label that neutral. Going to label that line. Now, a run capacitor with a dot and without any switching device, if it's straight to start, okay, we know it's a run cap. Okay, it's a run capacitor. There's two different types of capacitors. Again, for those who haven't had anything with motors before, we spend a lot more time on this. But just as an overview right now, there's two different types of capacitors. You have a start capacitor and a run capacitor. Okay, the run capacitor most often is drawn with a dot. Okay, that's part of the capacitor drawing. However, word of warning, more and more diagrams I'm seeing do not have that dot. Okay, we don't see it often in the newer equipment, because everybody who's working on the equipment should know that if I do not have any switching device, if this is a straight run through the capacitor from line to start, we know it's a run capacitor. We also know when we're working on equipment that run capacitors are metal. Okay? So run capacitors are left in the circuit when the circuit is powered. Now, there's a whole reason for capacitors, okay? And this is actually pretty important. Okay, when we have alternating current, okay, I've drawn this once before. I showed you a picture of this once already. You have what's known as a sine wave. Okay, and this is a really bad demonstration of a sine wave, but I've never claimed to be an artist. Okay, this bar in the central is neutral, or 0 volts. My peak, okay, up at the top, okay, the peak level, or the average peak level, which is probably fairer in the case of my drawing here, is 120 volts, and that's a positive 120. I also have a negative 120 peak, which happens down there. Okay, so I have a negative 120 peak. This whole thing happens 60 times per second. Okay, you make one complete revolution, positive to negative back to neutral, 60 times per second. That's what your household current is doing. That's why it's known as a frequency of 60 hertz. Okay, when this passes through 0, it's a split second through 0. It doesn't stay long in 0, but it's enough to make my motors inefficient. Every time this passes through 0, I do not have any voltage being applied to the motor. Okay, now the motor is a coil of wire. What happens when I put power on a coil of wire? Anybody? What happens when I put power on a coil of wire?
It energizes.
Heats up.
I heard it energizes. Yeah, that's true. But what does it do
It heats
with
up.
that energy?
Gets a magnetic field.
It creates a magnetic field. Okay, so if I create a magnetic field, okay, I basically have a magnet. One side of this magnet is north. one side of this magnet is south. Now, a motor is built with magnets in it. The motor itself has magnets in it pre-manufactured at the factory. Magnets have a north and a south pole. Okay, so this is what causes the motor to start spinning, is as I'm building a magnetic field in here, okay, all of a sudden I might have a north field. 60 times a second, that changes to a south, and then back to a north. Also, this magnet in the motor is spinning. So I have two rotating magnetic fields. What happens when you put a south and a south pole towards each other of a magnet?
They repel.
They repel each other. When you put a north and a north together, they repel each other. Okay, well, if it's anchored on a shaft of a motor, when they repel each other, it's going to turn the shaft of the motor. By the power going from a positive to a negative 60 times a second, okay, it's going to continue to repel each other. What happens to the magnetic field when it is in the zero position, when it is basically just at neutral? What happens to the magnetic field?
Is it gone?
It stopped.
It's gone for a split second. So how efficient is that motor turning when there's no magnetic field?
Not very.
Not very. Okay, what a capacitor does, okay, a capacitor blocks DC power and passes AC. Okay, in other words, it blocks DC and passes AC. In the process, the capacitor delays the current to the start winding. Okay, anywhere between, it's considered anywhere between 30 and 70 degrees out of phase, which means that it's sort of lagging in the peak, but it's also lagging if I draw a point in time here. If I just take a line and draw a point in time, my start winding and my run winding, which is the green, is not ever going to be coming through zero at the same time, because time goes on. So my start winding and my run winding, if I'm using a capacitor, will never be coming through zero at the same time. So if I have 0 volts on the run winding and my magnetic field has collapsed for that split second because it's changing from a north to a south or a south to a north, my start winding still has a magnetic field that is still going to continue moving that motor. It's not as strong of a field because the winding's a little bit different, but it's still going to move that motor. Does anybody have a question on that? That's the whole reason we use capacitors. It provides that extra power, okay? It provides that extra jolt, and it provides that extra energy to make these motors more efficient when they're running. And if it's just a start capacitor, it provides the extra energy that's slightly out of phase to start the motor turning. Okay, it all has to do with how our sine wave works. So, seeing this, would a DC motor have a capacitor?
No.
No. Direct current motors do not have capacitors, and you're starting to see those more and more in HVAC equipment. Direct current motors do not have capacitors. So if you walk up to a system, okay, if you walk up to a furnace and the blower motor does not have a capacitor, it's a direct current motor. Okay, it's going to operate slightly differently from the AC motors. So as I'm going through this, and as we're talking capacitors, we're strictly talking AC motors. Now on large equipment, large commercial equipment, you may not have a capacitor on a motor. Okay? We're not talking about it right now, but you have three-phase motors. Okay? Three-phase motors don't have capacitors. They're built differently. And again, three-phase, you will never have two legs going through zero at the same time. Again, it has to do with the sine wave. You cannot have two windings of the motor going through zero at the same time, or that motor is going to become very inefficient. Okay, so that's the capacitors. Now, back to this motor diagram. Thermostat calls for, in this case, let's make a slight change to that thermostat. Let's make it into a heating thermostat, okay? So the thermostat calls for heat. It closes. It provides power to my run winding. At the same time, it provides power to my run capacitor, which slightly delays the current going to my start winding. Therefore, my magnetic field is going to be a little bit delayed in the change from north to south on that start winding. The motor turns, it runs efficiently because I never am losing my magnetic field. Common connects back to neutral. Pretty simple operation. Now, let's make a change to my schematic diagram that I started. Okay. I am going to change bulb 2 to the motor we just drew. Okay, let's get rid of bulb 2 and some of the components that went along with it. By the way, does anybody know the name of this motor that we just drew? What type of motor it is? Some of you guys will because you've had it before. Come on, someone take a guess. There's no wrong answer.
Capacitor start and run.
Okay, someone said capacitor start induction run. What would I have to have in this circuit if it was just capacitor start?
Start capacitor.
Oh, yeah.
And that switching relay, some type of relay, right?
Yeah.
What if I said PSC?
Yeah.
Permanent split capacitor.
Okay. It's a PSC, permanent split capacitor motor. The capacitor never comes out of the motor. Okay? It's always in the circuit. PSC motor. Now, in HVAC, our PSC motors have always been traditionally used on blowers, on the indoor fans. Okay, the blowers that are blowing the air through the ductwork. That has been the most traditional use of the PSC motors for years. I caution you, by the time you graduate and get through part of your apprenticeship, we're going to see very few PSC blower motors. So this is changing very fast. Okay, we are starting to see DC blower motors don't have capacitors on them. And they're called ECM motors, electronically communicated motors. So again, DC blower motors are called ECM, which is electronically communicated motors. Okay, they are becoming more and more frequent. The reason for this is where my PSC blower motor, when it's running without much of a load on it, might be taking 4 amps. The same ECM motor, okay, might be taking 0.3 amps or 0.6 amps. Okay, so there's a significant power savings with ECM motors. Okay, because ECM motors know when it needs to run at high speed. The motor itself controls based on the amperage being used, based on how hard it's working, how much power it puts into the motor. We can ramp up and ramp down a DC motor where we cannot do the same thing with an AC motor. Any questions on this?
No, sir.
Okay. So back over to my schematic. We got to put a motor in here. So we know it's a PSC motor. I just happen to have one drawn because I've never graduated like in 20 years or whatever it is. So we come back over here. We take my pre-drawn motor. I lost a wire. And we put it in here. I'm going to do some slight rearrangement on my connections just so it shows better. Okay. I need to draw another wire in here because for some reason I didn't copy all my wires over. So let's just draw my wire right there. Okay, so this motor we are calling our indoor fan. That's the part of the motor that's the part of the system that is blowing the air around the house. This is your blower motor. Okay? So this is my indoor fan motor. I'm going to change the contact name. Okay? Just because I like labeling stuff where they make sense. I'm going to change the contact name to fan relay. And I don't know why my system is deciding to do its little beach ball thing today. Okay, so I'm going to change that name to fan relay. What is the sequence of operation? Anybody? What is my sequence
your
of
service
operation?
switch closes, transformer is powered, then your SW switch is powered, powering your FR. FR then powers the run winding. Your heating thermostat calls, which powers your heating relay, which powers bulb 1.
Yep. Okay. So I basically just added the motor, the fan relay, and the indoor fan motor. Okay. So let's deal with the burner motor, which would be off of HR. Okay. HR is actually a much more complex component in real life than I'm showing here, but again, this is a step-by-step process. So what I want to do is I want to go ahead and change, I want to change the B1 to a motor. Now, in oil burners, we have two types of motors that are primarily being used in oil burners these days. The newer motors are all PSC motors. Okay, you're going to have a run capacitor on them. Some of the older motors are capacitor start, induction run. Okay, again, let me repeat that. The newer burner motors are all PSC motors, and that's what I'm going to work with right now. I'm not going to get into the capacitor start, induction run right now. The older burner motors, like the ones that are on furnaces and boilers that are 20, 30 years old, they are all going to be capacitor start, induction run. But as we've gotten more efficient, we want that additional capacitor in there because it really helps with efficiency. So what I'm going to do is I'm going to get rid of these two components there. I'm going to make room for my motor here. Okay, and I'm basically going to use the same motor that I just drew down there, okay, I'm going to put up there, we hope. Okay. I'm going to change its name, of course, because it's not an indoor fan motor. Okay, so I'm just going to adjust the sizing. When you copy one from another in PDF Expert, you always have to go back and adjust sizing. Okay. But this is now my burner motor. And I'm just going to label burn. Okay, so that's my burner motor. Okay, so now, knowing that's my burner motor, what's my sequence of operation? Someone different give it a try this time. What's my sequence of operation? Anybody? Okay, anybody give it a try, please.
Close the service switch, bring power to HR, FR on the transformer. At the transformer, go step down to 24 volts on a call for heat. Thermostat closes, power heating relay, closing HR, powering the burner. Close SW, powers FR, and powers the fan.
Okay, yeah. Okay, again, service switch closes. In other words, we have this whole system turned on. My transformer primary is powered, which provides power on my secondary. Okay, as long as the switches are in their normal position, which they are right now, nothing runs. My room cools off under the thermostat set point. My heating thermostat closes, powers my heating relay, which closes the normally open HR and powers my burner motor. Switch SW closes, powers my fan relay, closes the normally open FR, and powers my indoor fan motor. System runs until the thermostat satisfies and opens. Then something eventually is going to open my SW and turn my fan motor off. This is the basic oil burner system. We have more components we need to add, but this is basically what's happening in an oil forced air furnace. Granted, you're not going to have someone standing there closing the switch SW. We got to use some automation on that. Granted, we're missing a safety. Okay? But this is overall how it works. Questions? Okay, we're going to take this a step further, and we're going to talk about the automation of that FR. That fan relay, obviously, turning it on and off by itself isn't going to work too well, because someone's not going to want to be in the basement all night long and turn my fan relay on and off. So this switch isn't in a real-life circuit. What am I going to use in its place?
Time delay?
Well, I could use a time delay. That's a very valid answer. Let's hold that thought, but what else could I use?
Fan center?
Well, fan center is just a relay and a transformer.
A contactor?
What about a thermostat?
Yeah, thermostat. That's what I was going to say next.
Okay, what type of thermostat am I going to use?
Heating?
Okay, think about what I need it to do. Is it going to close on a temperature rise, or is it going to open on a temperature rise? This is inside the furnace, so I need to blow warm air around the room. Is it going to open on a rise in temperature, or is it going to close on a rise in temperature?
It will close on a rise in temperature and blow the hot air and open.
That's correct. So what you're going to use here is really a cooling thermostat, but you're just using it because it gives us the ability to close on a rise in temperature. Okay, so you're using a cooling thermostat, but only because it gives us the ability to close on a rise in temperature. Now that thermostat is going to be labeled as a fan switch. Okay, because it's basically designed to, as the furnace turns on, it's designed to once the furnace heats up, it's designed to energize the fan. Okay, that fan switch is part of a device that's called a combo fan limit switch. The combo fan limit has two temperature sensing devices in it. Okay, it has our fan switch to turn fan on. It also has a limit switch. Okay, so we'll just say limit, and that prevents the furnace from overheating. Why do I want to prevent that furnace from overheating?
It could cause a fire.
Yeah. Now, in what condition? What would have to happen for that furnace to overheat? What would be the What would be the point of the failure? Sorry, didn't hear that.
Bad airflow.
Bad airflow. So what would be my primary cause of failure or point of failure if my furnace is overheating?
The blower or the fan?
Yeah, the indoor fan or the blower might be bad or might not be starting. Okay, that's a repair. It's a frequent one. But even more frequent goes along with your lack of indoor airflow. What's another reason why you might not have enough air through that furnace?
Incorrect duct size.
Yeah, let's think simpler. Think way simpler.
Clogged filter.
Clogged filter.
Mm.
Okay, I go on about 10 or 20 of those calls every winter, and down here every summer. It's awesome to do a $150 service call and then charge $25 extra for the filter. Okay, clogged filter is by far the most frequent cause of a furnace overheating. Now, none of the other answers were wrong. Okay, bad airflow can cause a furnace to overheat. Okay, wrong ductwork size causes bad airflow. Yeah, a furnace will overheat. But your primary cause is basically incorrect filter sizing, and then a valid repair is the blower motor has stopped working. Gets old, things burn out with age. Biggest cause in parts of the country about blower motors not working, I don't think you guys have as much of a problem with it up there, but thunderstorms. Lightning strikes and high voltage surges kill blower motors. Okay, they're very bad on blower motors. Thankfully, you don't have a lot of lightning strikes during the winter months. So blower motor not working. Now, if I have a fan limit, if I have a limit switch that's designed to turn the furnace off if it overheats, where am I going to put it? Where in my circuit am I going to put it?
Before the motor?
So you're thinking between the HR and R?
Yeah.
Or between line and HR?
Between line and HR.
Okay, that is valid. I could put my limit switch in right there. Where else could I put my limit switch based on this diagram? There's one other place.
On the 24-volt side?
Be more descriptive. Where?
Between FS and FR, or 24-volt and FS?
Well, let's talk about your first one first.
Yeah, FS.
Because actually that was where I wanted to talk about that. If I open the path to FR, what am I going to shut off?
Oh, sorry, I'm looking at the wrong one. HR, right?
HR, yeah. Okay, because if I put any limit switch that interrupts the power to the indoor fan, I could make conditions worse.
Right.
Okay, so anytime I place a limit switch, I could put it here. You see a lot of times you see a limit switch on the line voltage side, or I could put it on the low voltage side, okay, which is getting more and more frequent. Okay, so I could put a limit switch on HR between line and HR, or I could put a limit switch after W going to HR. Personally, I like putting limit switches, okay, up on the HR side. Now, a limit switch, is that a cooling thermostat or is that a heating thermostat?
Heating.
I want it to open on temperature rise, right?
Yeah. Oh, that's
Okay.
cooling.
Open on temperature rise is the one that is a heating. So as it gets colder, it closes. Cooling, okay, is it would be a close on temperature rise. Okay, it would close as the temperature goes up. Now, a limit switch, is it normally open or is it normally closed?
Normally closed.
Yeah, because under normal operating conditions, the furnace isn't overheated. And I want that burner to run. So I'm going to take my normally closed switch and I'm going to put it in over here. We hope it goes in over there. Okay, and I'm going to label that sucker HLS for high limit switch. Okay. Why do I like putting it on the line voltage side? There's two specific reasons I like putting it on the line voltage side. Can anybody look at this circuit and tell me why? And it's okay to guess.
I have no idea.
Safety switch?
Well, it is a safety, but a lot of times we see safeties wired in series with my controls. But why do I like putting this one on the line voltage side?
In series with your motor?
You are right. It is in series with my motor. What could fail and actually cause my motor to continue to run if I put this limit switch on the low voltage side? What could fail?
Relay?
Yeah. What happens if my system is not calling for heat and for some reason, I'm going to do this in red. What happens if that relay fails in the closed position?
Stays on.
Stays on. Okay, I'd be very concerned if I had a burner motor that was continuing to run. Okay, there's just too much that can go wrong. That's why I usually try to put my limit switch on the high voltage side in the path of the burner motor. I see a lot of guys wiring the limit switches down. I'm just going to point to it with arrows because I don't want to confuse everybody. I see a lot of guys putting the limit switches right here. What's wrong with putting your limit switch right there?
You'll cut power to FR and HR.
Well, I don't mind it cutting power to HR.
Power is just being fed to it. There's no safety from the transformer.
Yeah. Well, basically, if I put it right here, if I put my limit switch right here, if that limit switch opens, I'm cutting out my fan relay, and I'm cutting out my thermostat. What type of thermostat requires power to run?
All.
I think back to yesterday when we talked about thermostats. There was a thermostat that I told you that loses programming.
Was it battery ones? Battery operated?
It's the thermostat without it's the digital thermostat without the batteries or with weak batteries. Okay, so I don't want to necessarily lose the programming of the customer's thermostat every time the limit switch opens. Customer could really care less about the limit switch opening, but if I lose power, they're going to really get upset over the loss of power because they have to reprogram their thermostat. Customers are funny like that. So I try never to cut power to a thermostat. Okay? Now, boilers. When we start talking about boilers later on this term, boilers use the high limit switch. It's an operating control as well as a safety. Remember I told you there's several different types of controls. Boilers use high limits as an operating control as well as a safety. Boilers, we set the high limit switch to about 190 degrees. I don't want the water to boil. I want it to be hot. Okay? So the burner actually comes on and off, on and off, on and off based on a limit switch. In forced air equipment, the limit switch is a safety. Now, is the limit switch a manual reset safety?
No.
You are correct. It is not a manual reset. Why?
It sets off on temperature.
Well, it shuts off on temperature, but why don't I need to have someone press a button to turn it back on? Why don't I want somebody to press a button to turn it back on?
Be wasting our time.
There's a bigger reason. What happens on a cold winter day to the inside of a house if there's no heat whatsoever?
You get triggered a lot.
Freezing pipes.
Freezing pipes and property damage. So even if I don't have a blower motor that's operational, okay, that furnace that's getting hot sitting in the basement while someone's out on their winter break to Vermont or whatever it is, okay, that furnace sitting in that basement is going to put off a little bit of heat, probably enough heat to not freeze the pipes. Okay, because heat rises. So that burner is going to put off a little bit of heat. That furnace will cool off just because it's sitting there. The burner is going to come back on. Heat the furnace up again to about 200 degrees, shut it back off. So that limit switch will allow that furnace to cycle but not get to a condition where it's going to catch fire. Do I want it running like that forever? No, I don't. But will it give enough where I have a chance of preventing a house from freezing? Yes. That's why we try never to interrupt heat as long as it's not a totally unsafe condition. And we're going to go into some totally unsafe conditions. But a blower motor going out, I can still safely operate that piece of equipment just on and off on a limit switch until somebody notices it. Any questions on this?
No, this is pretty hard.
Well, that's why I'm asking if there's any questions. Okay. This is, again, we now have our safeties in, we have our fan switch in, and I could draw this in different places, by the way. Tomorrow I'll show you another diagram with this drawn in a slightly different place. Okay, the fan switch can actually, I could not have a fan relay, and I could put the fan switch up here as well. You see it a lot of times just on the line voltage where I have the thermostat up here, and it's actually connected to the high limit in a way. It's called a combo fan switch that you can do both as line voltage. But this just happened to be one way you can draw it. I could have the fan switch thermostat, instead of on temperature, I could have it on time, using a time delay relay. More and more, and the reason I drew this down here originally for you guys, was more and more, this is not temperature driven. It's based on time. The furnace fires, comes on, and W feeds a time delay relay. Waits 90 seconds before it energizes the blower motor. Okay? After the furnace shuts off, that time delay relay waits another 2 minutes, continues to run the fan to get the furnace cool. Now, what temperature do I want this to come on? What temperature, roughly, do I want this whole blower motor to start?
200.
What's your body temperature? 200 is where I shut the high limit off. Okay, 200 I open my high limit. But where do I want the blower to start?
96, 98.
Since we're not going to tie it in that tight, how about 100?
That works.
Okay. I want it to start over your body temperature. Where do I want it to shut off? When it's done heating, where do I want it to shut off at?
About 140.
No, I still want it to shut off over my body temperature. Why do I want that range of on and off over the body temperature? Ever sit someplace and have a cold draft blowing down the back of your neck? Feels sort of uncomfortable. So again, as long as I start blowing the air through the ductwork at a higher temperature than your body temperature, I'm fine. Normally, by the way, whoever said 140 as a temperature, you're not wrong in remembering 140. When I turn blowers on, I normally come on at 140 and off at 100. Over 100 is my on. Off, I try to be around 100. Why do I want this little bit of a higher temperature coming on? What's the ductwork like when you first turn your furnace on?
Cold. Cold.
The ductwork's cold. I got to get that cold air out of that ductwork relatively fast. Okay. Any questions?
Nope.
Did I confuse everybody enough for today?
I just have a question. I just have a question out of curiosity. How often are you going to see this ladder diagram on a furnace?
This one is actually pretty frequent.
Okay.
But there will be some minor modifications. FS may be a time delay. Okay, your HR is going to be labeled something different because it's actually going to be a primary control, which we still have to talk about, okay? This diagram is actually a pretty frequent one with some minor modifications. Does that answer your question on that?
Yeah, thank you.
Okay, any other questions on this diagram? Okay, that's all that I have for today. We're ending about 10 minutes early, but I'm fine with that. I do read my email, so if anybody has any questions that you want to ask me later today, I'm fine with that. Just send it to me. I do have a couple appointments this afternoon with meetings and stuff, so I might not get back to you right away, but just let me know. Okay, and if you need any help with anything, let me know. Other than that, you guys have a great day.
You too. You too.